Okay, so this is part 3 of our lecture, and I'm introducing a total synthesis to highlight Evans oxazolidinones for aldol reactions, now that we've talked about their transition states and the mechanism. So this will be the total synthesis of Papamycin 621, and it was synthesized by Yikeng Wu in 2009 at the Shanghai Institute of Organic Chemistry. Papamycin 621 is actually known to exhibit antibacterial and antifungal activities. Let me write that down. And so there's been this huge interest in the molecule since the 1990s. Wu did a beautiful job at highlighting Evans oxazolidinone chemistry, and you can read about it in his Organic Letters paper. In 2009, volume 11. And if I haven't said it already, Organic Letters are really short papers. They're about 2 to 4 pages long. So they're meant to be a little easier to read, and it's really all organic chemistry, which is really nice. Okay. So let me go ahead and draw you the structure of Papamycin. It's a pretty big structure. So I'm going to go ahead and give myself a little bit of room. And please feel free to pause so that you can draw it as I'm going along. This is a methyl group. Okay, so that's the structure of Papamycin. It's a pretty intimidating group. It's got a ton of stereocenters, obviously. What Wu decided to do was to focus on the top part of the molecule. So let me go ahead and number it for you. And he started at the lactone carbonyl and moved his way over to carbon 18. Okay. But he specifically only focused on the following part of the molecule from 3 to 10 and the stereochemistry within those carbons. I think what's so amazing about this synthesis is that it's not obvious how you can use Evans oxazolidinone chemistry and aldol chemistry to synthesize this molecule. But he really does a beautiful job at highlighting that. And again, I'm not going to go over the entire total synthesis. If you want to see how he does put everything together, please go back to the ArcLED paper. I'm just going to focus on the use of Evans chemistry to introduce or start to introduce stereochemistry into the structure. Okay. And so if you go back, what you'll notice is that he breaks the molecule from carbons 3 to carbon 10. And so his target structure is from carbon 3 to carbon 10. And he breaks it down so that it looks as follows. Oh, excuse me. Let me redraw it. Oh, wow. Sorry. Okay. So this is his carbon structure, his target molecules, carbons 3 to 10. And what he does is he flips it over so that carbon 10, your aldehyde, is on the left side as opposed to the right side. So if I redraw it so that my aldehyde is on the left side, then of course my substituents at 9 and 8 are now dashed. And my substituents at carbon 7 and 6 are now wedged. Okay. This is his target. And the thing about it is that he flips it around, specifically if you remember from our previous examples from your homework set and from the total synthesis that I discussed in lecture number 2, part 2. When you're synthesizing something, you typically start from right to left. And so he slowly starts adding substituents from right to left, which is exactly how we're going to do it. Okay. That's the only reason why he flips it over 180 degrees. The other thing that I want to talk about is this group, and we'll discuss it a little bit more as we're going through the synthesis. TMS is trimethylsilane. And it is a popular protecting group for alcohols. Okay. Again, we'll talk about the conditions of how you put on these protecting groups, but these protecting groups are typically for alcohols because alcohols are so acidic and they're so reactive, they can oxidize, they can get deprotonated. And so in order to avoid all of that, you add protecting groups because you're going to continue with other transformations. Okay, so this is his target structure, and his starting materials are all commercially available, which is perfect. He can use the following Evans oxazolidinones, both enantiomers. He also has access to the following acyl chloride, which we've used before for our alpha alkylations. And finally, the following alpha beta unsaturated carbonyl compound is also commercially available. And so to start off the synthesis, again, remember, let me cut and paste this. We're starting from right to left. We're slowly going to walk our way towards the left and start adding atoms to that. He starts off with the following oxazoladenone. And just like in our previous syntheses, he acylates the oxazoladenone. So nothing new for us. He introduces his Lewis acid. And his base, followed by our carbonyl compound. And again, because you notice that we start from right to left, you can start numbering as dictated by your substituents in the target molecule, which means that this is carbon 7 and 8. Remember, if my substituent on my Evans oxazoladenone is dashed, it is going to give me the syn product wedged. And that's exactly what they observe. Oh, I want this in black. And so now I've got my wedged product. Let me continue to number so that we can keep track of all our atoms. We've got our alcohol. I can benzylate this. We saw this in our problem set. Benzyl bromide, triethylamine. Remember, again, your alcohols are pretty acidic. So all I've done is benzylate. Oh, excuse me. And you can see that it's starting to look like our part of our target structure. And see it highlighted. We've got our syn wedged product. Again, just like other Evans oxazolidinones or any Evans oxazolidinones, you remove them just like I taught you in lecture number 1. Anything that I taught you how to remove Evans oxazolidinone in lecture number 1 applies here. So if I treat this with lithium aluminum hydride and water, not surprisingly, I'm going to get my alcohol. He then oxidizes this with PCC to the to the aldehyde. Remember, PCC Chem 124 is a mild oxidant. And it oxidizes primary alcohols to aldehydes. Doesn't take them all the way to the carboxylic acid. Now that I've got my aldehyde, this is my new electrophile. Okay. Now I can move on to part 2 and introduce the remaining alcohols or the remaining carbon chain. Part number 2, which is carbons 9 and 10. Now, in this case, I want dashed syn products, which means I'm going to have to use the oxazolidinone with the wedged substituent. So just like before, I acylate. Nothing new. We've seen this numerous times. Just like before, I introduce my boron Lewis acid with base. Now our new electrophile is the carbonyl compound that we just made. Let me number it for you. Exactly same rationale as before. Once you add this, you are going to form the syn dashed product. Let me number these in red to stay consistent. And our product looks as follows. Okay. Just like before, I need to protect this alcohol, and this is where we introduce our trimethylsilane. Again, trimethylsilane. Your silicon is bonded to a chlorine in the presence of an amine base. The nitrogen deprotonates the alcohol, and once it deprotonates the alcohol, the oxygen attacks the silicon and kicks off the chlorine to protect your alcohol. Typically, we use different protecting groups because we, in general, want to do certain reactions to some alcohols, so some groups are easier to remove. Sorry, I forgot to put the TMS. I was busy talking. While others are harder to remove, which is fine, that's what we want. There's times when we want to remove one protecting group and leave the other one there. The silicon protecting groups are a little easier to remove than the benzyl protecting groups, and that's perfectly fine. It also has to do a lot with sterics. Benzyl protecting groups that are on primary alcohols may be easier to remove because they're less sterically hindered. So we typically add different protecting groups to oxygens so that we can selectively remove them and then do specific reactions with specific alcohols. Okay. And then just like before, he reduces to remove the oxazolidinone and oxidizes with PCC to generate the final target structure. And he's done with this specific part of the molecule. It's really clever because what you'll see is that the rings in the natural product, i.e. the 5-membered rings, are clearly made as you're going through the total synthesis. The rings are not initially introduced in the starting materials. It's not commercial. They're not commercially bought, and then everything is worked around it. They're actually made because he has to generate the stereochemistry first, right? And once he generates the stereochemistry, then he starts deprotecting alcohols, and then he starts making the rings. It's a really nice read. It is pretty thorough and overwhelming, so I've tried breaking it down as much as I possibly can. But it does follow other Evans oxazolidinone chemistry. Again, this is work that Evans pioneered. There is so much work on aldol chemistry using Evans' ideology and Evans' methodology. And so in our next part of the lecture, we are going to focus on the formation of anti-products using Evans oxazolidinones.